A 90-degree elbow connects a vertical and horizontal water pipe. Water discharges to the right. Assuming that the mass of the fluid can be neglected, determine the horizontal force needed to hold the elbow in a stationary position with an inlet velocity of 15 meters per second, an inlet diameter, of 40 centimeters, and an outlet diameter of 30 centimeters, and an outlet pressure of 200 kPa. So in this diagram that I've drawn up, we know the pressure, each diameter of the inlet and outlet, and we know the inlet velocity. We don't know the outlet velocity, and we don't know anything about the force, the reaction force, holding this element in place. We know that the mass of the fluid can be neglected also. And it says it's a vertical and horizontal pipe, so presumably this would be straight up going against gravity, and this would be horizontal. Now I went ahead and drawn the control volume for this problem. So at the inlet and the outlet, we have a pressure force due to the fluid flow. And I've drawn the control volume in such a way that the velocities are perpendicular to the control surface. That's very important in simplifying the analysis later on. And also whenever we pick a control volume and draw our forces on it, external forces, I got to have a coordinate system to reference. The positive directions of the coordinate system is very important. Now, in order to solve this problem, we're going to use the conservation of linear momentum. But if you're taking fluid mechanics, you're learning about Reynolds transport theorem. So this is Reynolds transport theorem, and essentially it states that the sum of all the forces, the surface and body forces on a control volume, is equal to the summation of these two expressions. Now this looks like quite a arduous set of terms, but whenever we make some simplifying assumptions, it reduces quite nicely. So in a steady flow system, where the flow is consistent over time, term 1 will equal 0, so we won't have to worry about this. And for the uniform flow case, we can rewrite term 2 as a summation over the control surfaces rather than the integral. You might remember from calculus that integrals can often be reduced to summations or approximated by summations. And that's the case here. Now, this expression is also equal to this expression if we draw our control volume way. I have this asterisk here indicating the stipulation. If we draw our control volume in such a way, as I mentioned earlier, that our control surface is perpendicular to our flow. In other words, the area vector coming out of the control surface is parallel to the velocity vector at the inlet and the outlet. This case here on the left is an outlet, so the dot product is a positive product of velocity and area magnitudes. And at an inlet case, the dot product is the negative product of the velocity and area magnitudes. Now, with those simplified assumptions in place, I have our simplified RTT equation here, where the sum of the forces is equal to the outlet change momentum minus the inlet momentum. Or really, I suppose you could call this a change in momentum summation here. Out minus in. Now for the x direction, here on the bottom left, our sum of forces is our reaction force x going in the positive x direction, and our pressure force going in the negative x direction. That would be this one. And if you recall how to get the force due to pressure, P is equal to F on A. So F is equal to P on A. F is equal to PA. And in the x direction, this is an outlet. So on the right-hand side, term 2, we have an outlet expression. V2 squared times rho times A2. Since there's no inlets in the x direction, only outlets, term 3 will be equal to 0. And from here, we can proceed to solve for what the problem asked for, the horizontal reaction force. I included the y direction, since oftentimes we might want to know the total force, not just the x force, but we do a similar process. So our sum of our forces in the y direction, we have minus Fy, and we have plus P1A1. There are no outlets in the vertical direction in this case, just an inlet. So term 2 is 0, and the inlet case holds a negative sign, since this is negative here. So we have negative V1 squared times rho times A. Now, let's solve for our horizontal force. So Fx equals P2A2 plus V2 squared rho A2. Now, we don't know the outlet velocity, but we know that this can be modeled as an incompressible fluid, so we can apply the continuity equation. To determine the outlet velocity. So we know Q1 is equal to Q2. In other words, V1A1 equals V2A2. So V2 is equal to A1 on A2 times V1 equals pi on 4 D1 squared divided by pi on 4 D2 squared times V1. The pi on 4's cancel. So our second velocity at the outlet is the ratio of the diameter squared times our inlet velocity. So I'm going to plug this in directly for V2 and rewrite it. Remember to square that, multiplied by rho times A2. Okay. Now, I'm going to factor out the A2 as well and go ahead and plug in numbers. So pi on 4 times D2. Let me move this down here. See it a little better. So factoring out the area, pi on 4 times 0.3 meters squared times P2, 200 kPa plus 0.4 meters squared divided by 0.3 meters squared times velocity at the inlet. So expression is squared times 1,000 kilograms per cubic meter, a reasonable assumption for the density of water. And we factored out our area term. All right. So I'm going to calculate this. Now, very important to recognize that this 200 kPa is the same thing as 200,000 pascals. So I like to type things in my calculator in base units. So I use pascals. And I did this wrong again. Thought I did this right. Oh, wait. Oh, okay. I did get the correct answer here. So the horizontal reaction force is 64,403 pascals. Or we could write it as 64 kilopascals. Now, if we wanted to solve for the Y force and get the overall resultant force, we would follow the same process and simply determine the overall reaction force. That's it for this video. Thank you all for watching. Please let me know what topics you're interested in, and let me know what you think about this video in the comments. Thank you.